Okay, well, hello everyone. I don't know where everybody is. Usually there are people already in chat, but okay. It is 3:30. That is when this class starts, right? And it's been one of those weeks, so I'm not always sure. And it's perfectly possible that I'm speaking to an empty room because I'm on at the wrong time. It's also possible that I messed up the setup for the chat. Um, so would someone say something, please, in there? No one? Bueller? Bueller? I have the right time. This is a 3:30 class, right? Okay. Yes, there are people. Okay. So yesterday, the reason why I asked is last night I messed up the chat system, and for calculus, so we're good. Okay, I just don't know what works. Okay, so hello everyone. My name is Scott Grisard from the University of South Florida. Today, this is discrete math, and today what we're going to do is we're going to start incursion, recursion, and induction. So what we're going to do is we're going to try to revisit some of these things that we've done before, and we're going to formalize them in terms of recursion. And we're going to kind of skip the and we're in the book, by the way. We are very much in the book. This is section 5.1, 5.2, 5.3 to 5.4. We're definitely in the book now. So if you want to read stuff, it's chapter 5 in the book. But we're going to skip this kind of shallow induction thing because it's not quite as useful for computer programming. So it's not as useful for using the math to build the algorithms. And that's the big theme, is that if we understand deep induction, then we understand how to program recursion and the other way around. So there are problems I want to solve as a programmer or as a script writer or whatever, especially if what I want to do is go over, I want to be looping over things, and then I want to go down recursively into lower directories. There are problems I want to solve that can be thought of as mathematical proofs with induction. And vice versa. Often I'll have a math problem and I'll start trying to write an algorithm to do the work, and then I'll figure out what's really going on with the process that needs to happen in order to figure out why. So that's kind of the idea, is that you can think of these recursive algorithms as an induction proof, or as part of an induction proof, or as not to say that they are exactly, but there's a tight, depending on the proof, whether or not how tight it is, but there's a correspondence between an induction proof and a recursive algorithm. So that's what we want to do. So I couldn't find a good picture. I suppose, one of the language guys should go there, like Chomsky or something. But here's the idea. So here's what we've been doing. Let's take, excuse me, my chair is doing something funky. There we go. So let's take some, let's take an example of what we've been doing. Okay. So this particular example, let me pull it up. So this particular example is called Pascal's identity. Let me make sure that's what it was called in the system, in the notes. Sorry, just making sure that I'm getting everything the same. So let's do an example of what we've been doing. So this particular thing is called Pascal's identity. Okay, and it goes like this. It says that n choose k equals n minus 1 choose k plus n minus 1, choose k minus 1. Okay? And we've been doing these proofs, okay, that go a bit like this. These are called the combinatorial proofs. All right? So, n choose k. Well, n choose k is the number of k items from an n-element set. So I'm going to use cards, because I always use cards, right? So I've got, let's see, 1, 2, 3, 4, 5. I've got, 6 cards, and I want to choose 3 of them. All right? So on the one hand, I could just count the number of ways to deal these 6 cards. Okay? So on the one hand, I could count the ways to deal the 6 cards. So here we go. Let A be a set of size n. Right? On the one hand, I could count the number of k element subsets of A. Okay? On the other hand, let little a be some fixed element of A. All right? So in this case, the 4 of hearts, right? I've got, this is the set A. My 6 cards is the set A. And now I'm going to take the 4 of hearts, and I'm going to pick on it. Now, I could count the number of ways to deal 5 cards, K cards, or 3 cards from this set of cards without the 4 of hearts. Or, right, I could, so this K element subset either has the 4 of hearts in it, or it doesn't, right? So I can count the number of ways there are to form the K subsets, right? The K element subsets, right? I can count the number of subsets of K size without the 4 of hearts as a possibility, or I take the 4 of hearts as a possibility as one of the items, and I count and then I count the number of ways to choose the other K minus 1 items. Okay, then A minus A as a set is the number, I should say it's not minus A, it's set minus A, right? This is A without the 4 of hearts. Is the number of K element subsets of A minus that right? So either it's in it or it's not. I said or I count. A minus A. Choose K minus 1. Counts the number of ways to form a K element subset of A where little a must be included. So if I add those two, so in both cases, I've counted. Oh, great. The same thing. Okay? So 1 to 5, how do we feel about this proof? Looks like 5 pulls down. Right, so I'm saying that these two things are equal, right? I can either count the k-element subsets of A, or I could count the k-element subsets that don't include little a, and then add the k-element subsets that do include A. Right? And when I look at this thing, I'm going to get a few 5s, but I'm going to get a lot of 3s, a lot of 2s, a lot of 1s. This proof is hard, right? It's one of those proofs where you have to sit there and go, does it work for 4? Right? How many cards do I have again? Right? So let's see. You know, I have to sit here and I have to do, you know, this and this and this. You know, so it's a hard proof. And this argument is unique. It only really works for this proof. Okay? And that's the idea, right? This proof is hard. You have to sit here and you have to think about it for a minute. Okay, well, let's see. Let's do a committee's argument, right? I've got 5 people that could sit on the committee. Okay? So what I'm going to do is say, okay, well, how can we do this? Well, on the one hand, you know, there's Scott, Emily, Suzanne, Boris, and Chitikov. Okay, so there's these 5 people that can sit on the committee. I need to pick 3 people to sit on this committee. On the one hand, right, I just count the number of ways to form this 3-person committee from the 5 people that I can choose from. On the other hand, I could count the number of ways to form the committee where Scott does not sit on the committee. So I need a 3-person committee from the 4 people that are left. Or I could have Scott be required to sit on the committee and then choose the other 2 people from the 4 remaining. Right? And you have to sit here and you go, I don't know. And it's a hard proof. It's true and it works. But you have to sit there and go, you have to think about it for a while. All right? Let's do another example. All right, let's do another one. Let's do not that one. I don't like that one. Let's see. I don't like that one. Let's do this one. All right, so let's do this one. This one's a cool one. So here's another example. All right. I want to prove that n choose 2 equals 0 plus 1 plus 2 plus 3 plus ... plus n minus 1 for all natural numbers opposants n greater than or equal to 2. So does everyone understand what we want to show? We want to show that n choose 2 equals 0 plus 1 plus 2 plus 3 plus blah, 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 all the way to n minus 1. 1 to 5, how do we feel about that thought? Okay. We've actually already proved this. Okay? So let me pull up the proof for you, because we've already done it. It's right here. Can I get it all on one go? Yes, I can. The proof is this bit of code. There's the code. Why is this the proof? This is actually the proof. Well, on the one hand, let's trace it. On the one hand, okay, when does m increment? Right? I'm going to go here. I've got this input, right? I've got this code. So when does m increment here? On the one hand, m increments never 0 times when I equals 0, 1 time when I equals 1, twice when I equals 2, ... n minus 1 times when I equals n minus 1. And remember, I started at 0, right? So this was one of the problem sets. Now, this is not problem set 9. This was actually on your test, right? Remember before I had this kind of print statement and I asked you, well, how many times it was going to print? And you said 10 choose 2 or whatever it was, or 4 choose 2 or whatever it was, right? That's actually what's going on here. On the one hand, I can do that every time this runs, right? When I get to 0, right? Here's I equals 0, here's j equals 0. Now, I get I plus plus, here I've got n plus plus, right? So if I equals 0 and j equals 0, right? J is not less than I, so it doesn't do this. And it just kind of keeps going and it increments j. Well, you know, it's going to keep going there. And anytime I do that, right? I is 0. So for any j here, it's never going to be less. So I'm not going to increment at all. Okay? So what happens here, oops, I closed it. I promise you it was up when I started. So what's going to happen here is this. So let's do screen 2. Documents. Math. Nope. This class is discrete. This is in problem sets. And so I'm going to ask it, and what was the name of this file? Triangle. I'm going to ask it for n to be 5. And look what happens, right? When everything was 0, m did not increment. When everything was, when I was 0, m did not increment, and so on and so on and so forth. Then I come down to here again. J is 0, I is 1. this time j is less than I. Okay? So what's going to happen is that this thing's going to increment. Here's j, and now j is less than I. So I increment m. Right? So if I equals 1 and j equals 0, I increment m. But then I don't hear. The next time I increment m is when I equals 2 and j equals 0. But then I'm going to do it again when j equals 1. So every time so the first time when I equals 0, I get no increments. When I equals 1, I get once. When I equals 2, I get 2, and so on and so on and so forth. Okay? How do we feel about that 1 to 5? Okay? So I'm going to have the conclusion that m counts 0 plus 1 plus 2 plus 3 plus 4 plus 5 plus ... plus n plus minus 1. Okay? By the way, the internet is doing something funky today. So I've had problems connecting and then getting disconnected and stuff. It seems to be working up, but not down, and I don't understand why. So sometimes people have been like sending me stuff, and it's going, it hasn't been loading YouTube videos, all that stuff. So, the internet's weird today in Tampa. Okay. On the other hand, m only increments for ij where I is less than j. But it always increments then. Okay? So that means for every set of the form ij, such as 0, 1, 0, 2, other way around, right? So it's, yes, 0, 1, 0, 2, etc. No, which should be 1. What's going wrong in this code? Oh, j is less than I. That's where I messed up. J is less than I. Okay. That means for every set of the form 1, 0, 2, 0, 2, 1, etc., m will increment. I know my head's in front of it. I'll tell you what, let's move this whole bit over here. Come here. On the other hand, it looks weird that it's now on the side. It's like a mad board thing, right? There we go. It still looks weird. Say Levy. That means for every set of the form blah, 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 m will increment. So m increments for every set, for every two-element subset of 0, 1, 2, ... n minus 1. There are n elements in the subset. In fact, it equals n. The set itself equals n. So m counts and choose 2. Thus, n choose 2 equals 0 plus 1 plus 2 plus 3 plus blah, 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 plus m n minus 1. Right? So, on the one hand, I count, 0 plus 1 plus 2 plus 3 plus 4 plus 5, blah, 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 n minus 1. On the other hand, this same algorithm counts and choose 2. 1 to 5, how do we feel about that? Exactly. I'm getting 3s. 4, 2. 4s, 3s, 2s. It's a hard proof, right? And the big problem is there's nothing really that I can take with me to use on other problems. Okay? There's another way to do this. Now, your book makes a big thing about the difference between shallow induction and deep induction. We're tossing that, right? Oh, no, this is not useless. There are times where you actually can't really get at an induction argument, okay? But you can do an induction argument. Now, a couple things. One, induction is hard. But it is the same hard from proof to proof. Okay? That's the first thing to know about induction. Induction is hard. It's not an easy thing to do. But once you get it, it's the same hard. All these proofs have the same hard. Right? This is section 5.1, I think it is. Okay? So I can recycle the hard part. The second is that induction shows me recursion, which shows me induction shows me how to code it. Okay? Because, this right here, this is math from code, right? I figured out why this was true by writing an algorithm and then working up here. Okay? Right, so I'm going to show you a bunch of examples. Okay? So this is what I did here. Now I'm going to use a completely different way to prove this. So here's how induction works. Remember that first proof, do a little dance, make a little love, get down tonight. That's what we're going to do. We're going to have some ground level. Okay? So here's how it works. We have some ground level. All right? We know is safe. Now, what we're going to do is we're going to stand on a ladder at some rung. And we're going to suppose every rung beneath it is fine. And by showing if every rung beneath it was fine, then the current rung was fine. Okay? But it's important that n is arbitrary, so it works for any rung on the ladder. And it's important to note that this is hard. Okay? This is hard. But it's a hard that you can use over and over and over again. So once you get the part that's hard, it's not only good for one proof, it's good for a ton of them. And it shows you how to code. So if you understand this one hard part of deep induction, you will understand recursion in coding. If you this is my promise. So here's my bill of sale. Here is the ad. If you understand the hard part of the method, you can use it again and again. Moreover, if you understand the hard part in the method, you will understand recursion in code. Okay, so people say that there are two really hard things about coding when you're an IT guy, right? So sure, you do object-oriented programming, but you don't have to have factories generating your objects. Our programs are usually not that complex, okay? Our programs, rungs on the ladder, what's the word after ladder? So it works for any rungs on the ladder. In particular, it works for the next run from the case I already know. I'm not sure what you're referring to now. Okay. So for our example earlier with A of A and K, is A all the rungs in the ladder? A the rungs we've already stepped on, in a sense, okay? I'm going to do an example here, and I'm going to do a bunch of examples here, okay? But here's the bill of sale. Here's the sales pitch. If you understand the hard part of the method, you can use it again and again on proofs. So there's only one hard thing, and it's a general hard thing. Now, again, there's this thing that the book calls called shallow induction. Now, you're going to leave here and you're going to go search the internet for induction, okay? Because this is hard. And I know it, you know it, the American people know it, even in his heart of hearts, you know, everybody knows that you're going to go use YouTube as soon as you leave here. But make sure that you do deep induction, not shallow induction, because shallow induction is different. Okay? The sales pitch. Okay? And then there's this note about what you're doing when you're looking up stuff. This is deep induction. There's this thing called shallow induction, which is easier, but it's not as useful. It's nowhere near as useful, especially for IT. We don't care. If we want to code something, we don't care about shallow induction. It's all deep. Okay, so just make sure that when you're looking up examples, that you're looking for examples that involve deep induction. Okay, so let's do the big example. Let's do what we had. Okay, so we had that n choose 2 equals 0 plus 1 plus 2 plus 3 plus ... plus n minus 1. Okay, now, the first thing I'm going to do is set up my base case. This is the ground that I know I'm solid on. All right, and n is greater than 2, by the way. N greater than or equal to 2. Greater than or equal to 2. So my base case is the ground I feel solid on, and there could be more than one. Okay? So it should be said that's base case, maybe case as. All right. So my base case in here is let n equal 2. So the first thing I'm going to do is prove this holds for n equal 2. Now, I only have one in this case. It's n equals 2. I'll get rid of the is. You can have more than one, but for the moment, I only have one for this one. Now, is this true for n equals 2? Well, let's see. N choose 2 when n equals 2 equals 2 choose 2. Oops. It does equal 2 over 2, but that's not the point. Equals 1. Well, 1 equals 0 plus 1. One to 5, how do we feel about that base case? Is it the case that 2 choose 2 equals 0 plus 1? Come on, you're wanting me on that? Is it the I don't mean to be making fun of you, right? 2 choose 2 equals 1. Are you on board with that? There are two ways to pick two cards. There's one way to pick two cards from a 2-card set. I take them both. Okay. And then are we on board with this idea that 0 plus 1 equals 1? I don't mean to make you feel bad if you're the person who wanted it. I stop at n minus 1, right? I stop at n minus 1, so 2 minus 1 equals 1. Okay? Because that's what the formula says, right? No, we're not in Z2. This is n equals 2. Okay? This is for any positive integer. N posant n is greater than or equal to 2. So let n equal 2. N choose 2 equals 2 choose 2 because n equals 2, which equals 1, which equals 0 plus 1, which equals, and I'll even do sum notation if that would make you happier, but equals that bit. So the idea here is that 1 equals 0 plus 1, and 2 choose 2 equals 1. Okay? If you want to see it in summation notation, and I'm actually going to put that, I don't want to confuse you if you don't understand summation notation, so I'm going to put that in green as in don't worry about it for right now. And probably don't worry about it, period. Okay? But it is there just in case you... in case you want to see it, it's there. If you like summation notation, there you are. So I have a base case. I know that for 2, it is the case that 2 choose 2 equals 0 plus 1. Okay. So that's my base case. Now my induction case. Assume for all m less than n, so let n be arbitrary. Okay? So I just want some positive integer greater than 2. Would we specify 0 plus 1? Yes, because I want to show this proof. If n equals 2, this statement holds. That's what I wanted to say. Now, I'm going to go over, I've got a ton more examples, but I won't be doing them. I'm going to do them next time, but I am going to go over today, and I'm just going to ask you to bear with me. Oh, I get to go to 5. Never mind. I might actually make all my examples. I'm looking at the clock. I'm like, wait, what time do I leave? Sorry, never mind. Okay, so well, I'm supposed to go to 4:45, not 4:15. Let n be, last semester, my course was one of those that ended on a 15, so my brain doesn't work about it. Let n be some posant greater than 2. Don't care what it is. What I want to show is if the theorem held for all m less than n, then it would hold for n. Okay? I want to show that if every rung below the one I'm standing on was firm, I would be firm. I can't spell beneath. Somebody spell that for me. Okay. So what I want to do is I want to scoop down. Okay. This is this idea. Okay. This idea is that I'm going to get down tonight. I'm going to go down into my previous cases. I'm going to find some way to make this n relate to the ones before it. Okay. So that's the goal. Find some way for this n to relate to what came before. All right. So here's what I'm going to do. Let me pull back up this thing here and change it back to this one. All right. So, suppose for any m less than n, now n is the one I'm at, m is everything that came before. M choose 2 equals 0 plus 1 plus 2 plus ... plus m minus 1. Okay? So suppose that was true. This is actually, formally, this is called the induction hypothesis. Okay? I'll label that. Because when you Google this, and you will, you're going to want the fact that this is called the induction hypothesis. And that's the induction hypothesis. Now, all right, so now I'm going to look at n. N choose 2. Well, what does n choose 2 equal? Okay. Or I could start at the other end. All right, you guys don't like that? Let's start at the other end. 0 plus 1 plus 2 plus ... plus n minus 1. I'm sorry, n minus 3 plus n minus 2 plus n minus 1 equals what? Because this is what I want to show. I want to show that this equals n choose 2. But notice here, if I go to n minus 2, I'm actually below the case that I'm talking about. 1 to 5, how do we feel about that? On this side here, if I go to n minus 2, I'm actually beneath this because this stops at n minus 1. Okay? So what I'm going to do is I'm going to let m equal n minus 1. Then my statement is now 0 plus 1 plus ... plus n minus 2 becomes m minus 1 plus n minus 1. So what happened here was every term here is replaced by every term here. 1 to 5, how do we feel about that? All I did was sub in, I let m equal n minus 1. Now the right-hand side of the thing I'm trying to prove has an n minus 1 here. This has an m minus 1 here, but that was for any m less than n. Okay? Since m is less than n now, this whole thing continued over. Since m is less than n, I apply the induction hypothesis. I know that this whole bit here is m choose 2 plus n minus 1. Okay. So what I did, and that's the really hard part, what I did was I took this whole string and I said, oh, that's m2. How do I know that? Because m is less than n. Okay, well, if that's the case, let's look at the formula here. Well, remember that this is actually n minus 1 choose 2. So this is n minus 1 choose 2 plus n minus 1. Because that's what I had here. Suppose that for any m less than n, this is true. And I let m be n minus 1, so m is less than n minus 1. I'm sorry, m equals n minus 1, so m is less than n. How do we feel about that little bit of statement? Since m equals n minus 1, m is less than n. Ah, but it's not. Oh, because I just subbed back in m. M equals n minus 1. The n minus 1 is coming because I let m be n minus 1. So since m is n minus 1, I just sub back n minus 1. Okay. Well, I got it as part of the answer that equals this statement. These two statements are equal. This statement here equals that by the induction hypothesis. So here, I'll move this here. That might help you better. If this appeared next to this, would that help? And I'm not saying this isn't hard. This is really hard. And then this equals that. Okay. Well, n minus 1 choose 2. I have the formula for that, right? So let's put that in. So I've got n minus 1. Oops, that was n. N minus 1 times n minus 2 over 2. And I've got this plus n minus 1 hanging about. Okay. So let's take a common denominator. And I get n minus 1, n minus 2. Let's see. I don't need that there. Plus 2 n minus 1 over 2 over 2. All I did was take a common denominator. And that equals n minus 1, n minus 2, plus 2 n minus 1 over 2. Okay. Well, now I'm going to factor out the n minus 1 from both terms. And I wind up with n minus 1 times the quantity n minus 2 plus 2. No. N minus 2 plus 2. That equals n, doesn't it? Well, n times 1 times n, that's n falls 2. And that equals n choose 2. So, if I hold for all m less than n, it holds for n. Okay. Well, I know it holds for 2. So I should say the base case, by the way, between that. So it holds for 3. Since it holds for 2. All right, if it holds for every m between 2, my base case, and n, okay? Well, it holds for 3, therefore it holds for 2. I'm sorry, it holds for 2, therefore it holds for 3, right? It holds for 3 since it holds for 2. Well, it holds for 4 since it holds for 2 and 3. N times n minus 1 is the definition of n falls 2. Yeah, right? It holds for 5 because it holds for 2, 3, and 4. Well, it works for 6 because it worked for... Right? Well, it works for 6 because it works for 2, 3, 4, and 5. And so on and so on and so on and so on and so forth. 1 to 5. How do we feel about that? That's the hard part. The really hard part. Now, some of this algebra is difficult, but this is what I mean by the hard part. What did I do? I said that if it holds for everything the need. Why is that the case? I know it holds for 2, right? Well, where is that point? Give me the point where it doesn't work. So someone is saying, what is to say it will reach a point in which it's not true? Well, if the point was 1,436, let's suppose it did not hold for 1,736. Yes, for 1,736. But wait. It held for 1, 2, 3, 4. I'm sure one's not included. Sorry, 2, 3, 4. 1,735. Now look at what I proved. I proved that if it held for any m less than n, that's what I assumed, right? I assumed that n was some positive integer greater less than 2. Now, if it holds for any m less than n, then it must hold for n. So since it holds for 2, 3, 4, blah, 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 1,735, it must hold for 1,000. Right? In any absurd number, this trick works as long as that number is finite. The number of atoms in the universe is really, 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 really big. Still a finite number. Infinity still laughs at that. And this is one of the powers of mathematical logics. When we say every case, we mean every case. I can assert it always works because it always works for the successor, right? if it works for all of the predecessors, if it works for every n below, then it works for n, right? So if it works for all the predecessors down to a point, it works for that successor. All right? And I'm able to assert that it always works. I'm able to assert that there's some ground I can stand on, right? I have to find some ground I can stand on, and then I have to find out that if it works for all the rungs below, then it works for the rung I'm standing on. Okay? Now, it's hard. So someone's saying, if I climb a ladder with 100 rungs, why does the 98th not rung when I step on it, just because the second rung I stepped on doesn't break? Well, that's not it. The 98th rung does not break when I step on it because the 97 rungs before it were firm, and I know that if all the rungs before me are firm, then the rung I'm standing on is firm. Okay? And it's hard. It's a hard thing to wrap your brain around. But once you wrap your brain around this, once you play with this enough and work on it, it's really powerful because it's the really hard part of all of the proofs. Well, I mean, there are other hard parts to them, but it's the really, really hard bit. What's more, I can use this to code. So suppose So let's say I wanted to write a function to compute n choose 2. Right. So it doesn't say all rungs in the future works. It says the one I'm standing on works. But the one I'm standing on could be anything. And that's the point. For any natural number that you pick, I've shown that I can go back all the way. Right? So the point is not that I'm building up, right? Regular induction, you see this metaphor all the time about the ladder. Weak induction builds up. Strong induction scoops down. And that's what I want to do. And the reason why I want to scoop down is because that's recursion as well. Okay? So by scooping down, by saying, okay, I'm standing on n, if everything below me works, I work. All right? And remember, n's arbitrary. So I can make it so if you want the proof for 500,736, I go, okay, well, that's going to work as long as the rungs before it works. So if I have the rung before it working, then I've got this rung working. Well, that one will work if this one does. 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 Blah, 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 all the way down to 2. Okay? And the point is that this one works if this one works, 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 all the way down to some case I knew worked. And I know it works for 2. So if you're on rung 98, well, that'll hold if rungs 2 through 97 hold, which will hold if rungs 2 through 96 will hold, which holds if rungs 2 through 95, blah, 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 which holds if rungs 2 through 3 hold, which holds if rung 2 holds. And there was that if. That last if, it works if rung 2 holds. So if rung 2 holds, it works for all of these ifs. And I proved rung 2 held. Okay? And this is weird. This is weird. This is strange. This is recursion. Right? This is induction, strong induction / recursion. They're the exact same thing. And let me show you what I mean by their exact same thing. I want to write a function to compute this. All right? So I wrote one before that had these while loops and all that other stuff, and it was a pretty long, decent-sized function. Okay. Now, if you get over the fact that I put a bunch of error checking code in here, you see it. This function that does the exact same thing. Oops, I didn't want to do that. Here's a function that does the exact same thing. And let me show you how many rows of code this actually is. All right. So let me write a function that computes n choose 2. All right. Function choose 2. It takes an integer n. If n is equals 2, return one. Else, return now. So, what does that do right here? What did I just say? If n is 2, return 1. Base case. Now, where did I do my induction hypothesis? Where did I sub in? I subbed in m choose 2 right here. And then I added, so right here is the key step. Here is where I used what came before. All right. So there's a question about, it's true that 1 through, but I have not tested none of the other rings above 98. But if I'm standing on 1007 and I know that the rungs 1 through 98 work, I know that the rung 99 works, which means I know that the rung 100 works, which means I know that the rung 101 works, which means I blah, 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 and I know that 1007 works. Okay? And let me show you how. This, I think, will help. This was the key, right? This is where I subbed in. So now, this is recursion. So notice in induction, here I use the inductive hypothesis. Where I use the inductive hypothesis, I'm going to put in the function itself. And I'm going to scoop down there. Return, choose 2, n minus 1, right? I went down 1, and then I'm going to add n minus 1. Now, how many lines before, and I'll show you why this works. Now, how many lines before did I have to do in order to do this? 20. Okay, so not all of these lines here, but I got 2 nested while loops. I got a bunch of variable declarations. I've got, the actual code itself, right, without the error checking is 1 line, 2 lines, 3 lines, 4 lines, 5 lines, 6, 7, 8. This is error 9, 10, 11, 12. Basically, it's 13 lines. One, 2, 3, 4, 5, 6, 7. Okay. Now, let's look at that code all typed out nice and neat. Or at least let's try. There it goes. This is that code in PHP. All right, so let's look at this for a second because this is kind of cool. So before, when I ran this, and yes, I will post this code. Yeah, I'm about to return a method, but I'm not returning a method. I'm returning a call to the method. Okay? I'm calling the method again. So this is going to scoop down for me. Now, before, I ran this with 5. Let's do this new and improved version. And look what happened. I started with n equals 5. All right. I had n equals 5. I started this program, right? It chose 2 with n equals 5. That's that first call. N did not equal 2, so it called itself again with n equals 4. Then it called itself again with n equals 3. Then it called itself again with n equals 2, and then it finished and it added all those numbers together. So this is how the induction worked. My head's in the way, isn't it? This is how the induction worked, right? I was at 5. I needed to check 4. Well, I needed to go to 3. I needed to go to 2. Oh, wait, I'm at 2. There I'm firm. Ba-boom, 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 ba-boom. How do we feel about that 1 to 5? And it should be noted, that's hard, this concept. This is why recursion is so hard when you're trying to learn how to program. Now, there's other stuff that's hard, right? I can have machines that create... Who in Java created the factory idea? I've got an object that's going to be a factory object that's going to generate new objects of all these sorts of things. And then I'm going to inject code into the thing. So I'm going to do... That's not theoretical computer science, right? That's kind of... I don't know if it's even practical computer science. I mean, Linus Torvalds wrote... And not that I'm opposed to object-oriented programming. Object-oriented programming is awesome. Okay? I'm pro object-oriented programming. But this idea of having factory classes that generate classes of their own? Okay. Factory objects? I don't understand the point. But I'm not a professional programmer. I'm a mathematician. IT guy. I don't understand the point. Okay? Linus Torvalds wrote C without a single wrote Linux without a single object in it. Okay, so I don't, I get the point about using object-oriented programming, but it's a little unnecessary. Recursion? No, you need that. You need recursion. Okay? Yes, so that is what the thing is calling. It's doing 2 minus 1 plus 3 minus 1 plus 4 minus 1 plus 5 minus 1. Okay? Now, again, let's do this with 10. Well, what did it do? It called n equals 10. Well, okay, it called this, it called this, it called this, it called this. Let's actually do right now what someone just posted in there. Let's make it echo that, right? Echo. I'm going to echo the statement that's actually going through the computer's head. Choose 2 dot n minus 1 dot plus Oops, I can't seem to make the other thing go. Plus n minus 1. Oops. Dot. All right. And then I'm going to say return. All right, let's actually echo that call. There. I think that would work. Oops. A non-numeric value encoded in line 23. What did I mess up? Dot n minus 1 dot quote dot n minus 1. I bet I need escape characters for some of this. Let's try literals. I bet there's something in there that needs to be escaped, and I don't feel like looking it up. And choose 2. What's it saying? Minus 2. So I've got an n. Is it doing it always, or is it only doing it with the thing? So let's do 3. Okay, well, my guess is there's something in here I need to escape. Let's just try print, because maybe echo is the problem. Let's do that. Close that. Those should all be strings now. No. Okay, so something in here is not working it, so let's do print. Choose 2 here. Let's stop there. See if that's the problem. Oops, wrong way. Is that what it is? Probably. Nope. Unexpected. Okay, you're a commented thing, so I don't know why you're upset. Oh, you're upset because I didn't put a parenthesis there. Someone's telling me it's the semicolon. So yep, that's it. DDD. Let's get rid of those comments and let's. Can I escape a semicolon? Not with a double quote. Let's just get rid of it. There we go. Nope. Oh. If you think it takes a long time for you to do your thing, yeah. And let's see, we probably want a break here. Choose 2 called with, it's still doing it. Something here probably requires escaping. If I get rid of the plus, does that do it? Nope. I don't know why it's doing that. A non-numeric counter, PHP, -1. Why is it doing negative? Oh. Return, choose 2. This is the problem. Why is that the problem? Oh. That's the end. There it is. I needed to put those in parentheses. It's probably going to do an error again. Expecting, comma. This shouldn't be there. There we go. Now it works. So now if I call this here, right, it's going to tell me what I did, what it did every time, right? It returned choose to 2, and I need the plus back because I took it away. Here's what the recursion did. There we go. Okay, so how do we feel about that 1 to 5? Okay. So the idea of this was that what I'm doing is that I'm going through, this code is scooping down. And I will post this code, by the way. So the big idea is that what I'm doing is I'm scooping down. And you can see what the computer's doing. It's actually going down and down and down and down to kind of dig this out. All right. Now, this is hard stuff, so don't feel bad if you don't have it right away. But do work at it. And I'll post some I'll post the quiz with a few of these problems, with some, thoughts about these things. Okay, so today, what we did was we introduced recursion. Introduced induction and recursion. Okay. I need to be back on the other one, don't I? Okay. Next time, more induction and recursion. Okay, because we're going to do this. We're going to do a couple more proofs like this. We're going to do the proofs about, we'll do some prime number proofs that are very nice. And then we're going to prove the binomial theorem again. But instead of this hard argument, I mean, it's not the easiest argument in the world, but instead of this hard way of doing it, we're going to do it with recursion. And that's always a cloud breezer. Are there any other questions? Comments, issues, suggestions, thoughts? Okay, well, that's it. I will try to get the problem set up to you shortly. I have to modify it because, we kind of missed stuff. Yes, you can send me direct messages if you've got questions and other things of that nature. And I will be posting this. I can't believe I let it go a week last time without posting the video to YouTube. And I will be posting notes and the examples that I did in class in code. Thank you.